Hi everyone, I'm Julia Tan, and today I'll be presenting our work on optimal transport policy fusion for learning diverse skills. Intelligent systems are increasingly penetrating into real-world applications, incurring the need for sophisticated models that can perform ever more complex and adaptive tasks. Recent advancements in reinforcement learning have extended the capacity of neural networks into the physical domain. However, most real-world applications require numerous specialized capabilities. The computational resource constraints associated with sample inefficient training, combined with the complexity of redesigning the appropriate reward structures for each capability, make it difficult to achieve solutions for varying goals in a reasonable timeframe. Accordingly, we wish to develop a minimal dependency method of leveraging the learned behaviors of existing policies for learning new skills. We propose a post-hoc technique to fuse independently trained IROS policies represented as neural networks using optimal transport theory. The goal is to generalize the prior knowledge of parent policies over different environments as well as different robot kinematics to create a Renaissance agent capable of learning new skills more effectively and within a shorter time period than either retraining the parent agents or training a new agent from scratch. When training a policy, an RL algorithm is used to update the weights of the neural network so that the cumulative reward is maximized over time. Depending on the task configuration during training, these learned weights will differ between agents. However, for policy networks that have the same input features, similar weight vectors at each individual layer may represent common learned patterns. By considering the two sets of weight vectors as probability distributions of Dirac masses, we can formulate an optimal alignment such that the neurons most likely to represent common patterns are matched prior to fusion. A one-to-one similarity is computed via a transportation cost matrix, which is generated from minimizing the cost of moving a weight vector in the source model to the position of a weight vector in the target model. Since this cost represents the Earth mover's distance between the two vectors as distributions, the smaller the distance, the closer the similarity. So we can match the neurons of the source model to the neurons of the target model by transporting them according to this optimal map. For each subsequent layer's weights, we rearrange the vector elements to correspond with the new alignment of the previous layer before applying the same process. Finally, we merge the aligned neural networks by averaging. Before showing the actual robotics experiments, let me first demonstrate the high-level idea on an image classification problem. For this proof of concept, we will use the MNIST dataset and a neural network with two hidden layers. The first model is trained to classify zeros versus all other digits, while the second model is trained to classify ones. The desired new task is to be able to recognize both zeros and ones versus all other digits. After applying the proposed technique, the fused model without additional retraining was able to correctly classify some of the required digits, but not all. However, after retraining, the test accuracy significantly improved to around 98%. For 10 training epochs on the new task, it was found that the fused model, shown in orange, reached higher sustained accuracies much faster than the benchmark models. Let's now extend this from a classification problem to reinforcement learning agents. The first reinforcement learning task we will be training on is reacher. The goal is for the end effector of the robotic arm to reach to a randomly located target and stay there. The first policy is trained on targets placed only within the first quadrant of the workspace, while the second policy is trained on the second quadrant. Since these configurations of the robotic arm are quite different kinematically, the learned capabilities of each agent are limited to actions within a single quadrant. The desired new task is to reach targets within both the first and second quadrants. The fused agent initially struggles to reach to any targets. However, from the classification problem, we know that the model should improve significantly after minimal retraining. After retraining for another 500,000 time steps, we can see that the fused agent now performs much better. Furthermore, we can see that the fused agent shown in green achieves consistently higher rewards faster than the other benchmark models, particularly compared to the new agent being trained from scratch. Extending this reacher task to the 7 degree of freedom fetch robotics arm, we can test on a more complex agent, observation, and action space. Since the fetch robot now stands above the workspace and moves in 3D, the existing problem formulations are modified to ensure that the parent policies will learn distinct behaviors. So instead, the first policy learns to move the end effector over the bottom left of the workspace, while the second policy learns for the top right. Now let's change the problem scope to target positions that are located anywhere over the central region of the workspace. After retraining on the new domain for 200,000 time steps, the fused agent is able to quickly and consistently reach to the targets. Once again, the fused agent shown in green achieves such performance much faster than the other benchmark agents, surpassing minus 2.5 rewards per episode by 25,000 time steps, while the next best agent takes approximately 100,000 time steps. Now let's consider two agents trained on the same task configuration, but this time with different kinematics. In the walker task, the goal is for a bipedal agent to walk forward as fast as possible. The first model is trained with the more powerful torso-connected foot, while the second model is trained with the more powerful left foot. We can reformulate the target domain to learning the walker task on an agent with equally powerful torso-connected and left feet. After retraining on the new domain for 500,000 time steps, the fused agent is able to walk forward in a natural-looking manner. In contrast, both parent agents do not show any prolonged improvement as a result of retraining, supporting the notion that they are over-optimized to their respective original domains. The fused agent shown in green is the only one that achieves high consistent performance by the end of the retraining period, surpassing 1,000 rewards per episode. Extending to a more complex agent, the half-cheater task involves a quadruped robot with the same goal of running forward as fast as possible. The first agent has greater thigh and shin power but reduced foot power, resulting in more rigid foot joints. The second agent has the opposite kinematics, resulting in more rigid thigh and shin joints. Like before, we changed the target domain to learning the half-cheater task on an agent with neutral power for all joints. After retraining on the new domain for 500,000 time steps, the fused agent is able to run without any of the joint rigidity displayed by the parent agents. Moreover, the retrained parent agents still exhibit very similar kinematics to what they had learned from their original training domains, despite the change. This demonstrates how the fusion technique is useful for consolidating the common knowledge of parent policies, which have been over-optimized to a previous task, to allow for learning diverse skills more effectively. Ultimately, the fused agent shown in green not only performs quantitatively better by the end of the retraining period, but is empirically more adaptable to factors such as gait style beyond reward maximization alone. To summarize this work, we have developed a post-hoc policy fusion technique using optimal transport theory to create Renaissance agents, which can learn new domains more effectively with minimal retraining. A promising future application of this technique is in simulation to real policy fusion, allowing for more complex or risky policies to be trained in simulation, then adapted for the new domain of real hardware with significantly less effort. Consequently, we could mitigate the sample inefficiency and cost of gathering real-world data, as well as the safety concerns of applying the trial and error approach of RL on real robots by considering the similarities between various policies in sim and how they might be generalized for the real world. While this appears comparable to domain randomization, it would be more powerful in leveraging independently trained policies instead of only a single policy trained under variable rendering. I would like to thank my co-authors Ransalu, Senanayake, and Fabio Ramos for their guidance on this work. Thank you.